In the following two provided examples on the left and right, you're required to test symmetry for the x-axis, y-axis, and the origin, and also to find the x and y intercepts if they exist, as well as sketch the graph using the information that you've derived. So in the first equation, we have y squared minus x squared is equal to 9. First, we're going to test the x-axis symmetry. X-axis symmetry, as was noted in the previous video, requires you to negate the y and see if you get the same equation as the given left side provides, right? So if you have the same left side y squared minus x squared after negating the y, that means there is x-axis symmetry. All right, so let's try that. So we're going to negate the y. I'm going to square that. And then here's what we get. We get y squared, right? Because the negative squared is also positive. So we get y squared minus x squared. Good. So that means this matches the original left side, right? So that means this graph has x-axis symmetry. Now let's test for the y-axis symmetry. Now instead of negating the y for the y-axis symmetry, we're going to negate the x this time. So we're going to keep the y as it is, y squared, and then minus negative x squared. So what we're getting is y squared minus, and then minus here gets squared, it gets to be positive, right? So x squared like that. Bingo. So that means there's also y-axis symmetry because this equation, this left side, matches the left side of the original one. Now for the origin symmetry, we need to negate both y and x, right? So let's do that. Minus negative x squared. That's equal to y squared because the negative gets to be positive when squared. Minus, and then again the negative for the x, it's part of something that's being squared, so that's going to be positive x squared. So as you can see, all three symmetry tests yielded positive results, meaning that this graph is going to be symmetric with respect to x-axis, with respect to y-axis, and with respect to the origin. Sounds unusual, right? But it's true, it's possible, and you're going to see when we plot this. But before we plot it, we have to find the x or y intercepts if they exist. Now when it comes to x-intercepts, you have to understand x-intercepts are points on the graph that are at the same time on the x-axis, right? Points at which the graph crosses the x-axis. These are called the x-intercepts, right? And the x-axis points always have the y value equal to 0. So essentially what you want to do, you want to set y is equal to 0 and then solve for x. And this way you will find the x values with the y value of 0 that will give us the coordinates of the x-intercepts if they exist, right? So we're going to, instead of the y, we're going to substitute it with 0. And then minus x squared is equal to 9. So that means 0 is there, so minus x. What this does is that minus x squared is equal to 9. And that means that dividing by a negative 1 gives us x squared is equal to negative 9. Now this has no solution. Why do you think this has no solution? Because if you square root both sides, x would be equal to the plus minus square root of negative 9. Is that allowed? No, right? Because you can't have a real number, a real negative number inside the radical, right? It's not going to give you a real number result, right? So this has no real solution. So we're just going to write no solution. We assume we're talking about real, so we say no real solution. Thus, what this means is that there are no x-intercepts. Right? Because we didn't find any solution. Thus, there are no x-intercepts. Now, let's test for the y-intercepts. The y-intercepts, as you might have guessed, deal with the y-axis intercepts, right? The y-axis. So it means we will need to find points on the y-axis at which the graph of the set equation yx squared minus x squared minus is equal to 9 crosses the y-axis, right? We need to find the coordinates of those points. And to do that, you realize that on the y-axis, the x value will always be 0, right? It's the vertical values, the y values, that are differing. But the x value is always the same, right? It's always going to be 0, no matter what happens on this axis. So essentially what you want to do, you want to substitute x with a 0. So y squared minus, this time x will be 0, is equal to 9. So what that does, that lets us have y squared is equal to 9. Square rooting both sides would solve for 9, but would give us plus minus the square root of 9, which is 3. So what does that tell you? It tells you that there are actually two y-intercepts, right? Because the first y-intercept, so y-intercepts at, the first one is 0, comma, positive 3 for the y value, and the 0, comma, negative 3 for the y value, right? And just to bring your attention, this 0 is the 0 we had here for the x, so that you know where that came from. That 0 for the x makes sure that you stay on the y-axis, right? That you're not anywhere else but the y-axis. And the positive or minus 3 here just tells you where on the y-axis you're going to be, vertically speaking. Right? So let's plot those points while we're at it, because that's good, right? So we have a point here, 0, comma 3, and 0, comma negative 3 is going to be here. Now, if you test some values to see where the graph goes from those points, you can try to test 1, for example. Test the x value of 1. Now here's where it comes special. X is equal to 1 and x is equal to negative 1 will give you the same y value, right? Because the x is squared, essentially, right? So x is equal to 1, x is equal to negative 1, y squared is going to be equal to 9 plus, because you would add x squared on both sides to solve for y, 9 plus 1 or negative 1, right? Which is going to be essentially 1. So that means y is going to be plus minus, because you would square root the y squared. You would square root the y squared. So it would be radical 10, right? Plus minus radical 10. So now let's understand something. Plus minus radical 10. First of all, plus radical 10 is definitely greater than radical 9. Radical 9, as we said, was 3, right? 3 is here. Radical 10 is greater than that. When you come to 4, it's going to be radical 16, right? Radical 16. So for the 1 value, radical 10 is going to be somewhere here. And also, as we noted, for the x value of negative 1, it will be also in the same vertical location. Okay, so definitely looks like the graph will be rising on both sides of this x value of 0, right? It will be rising. Okay, now now also keep in mind that we also have negative 3 here, and plus minus radical 10 also suggests that when x is equal to negative 1, we have to also plot the same thing here, right? Plus minus radical 10 means minus radical 10 is also positive, and that accounts for this side, for the quadrants 3 and 4 respectively, right? So the graph, now let's see. When you get to radical 16, you will get to 4, right? To the y value of 4. Now radical 16, how do we get to radical 16? We have to understand how to get there. We get there by having y squared is equal to 9 plus 7, right? So basically, when x is equal to radical 7, this thing will be 7. You add the 7, you get to 16, right? Radical 7 is still going to be less than radical 9, right? So it's going to be less than 3. but it's going to be greater than radical 4, right? So somewhere here, you're going to have a 4. Somewhere here. Okay? So for this x value, somewhere between 2 and 3, you will have a value of 4, right? Which will account for radical 16 plus minus radical 16. So you can create a mirror image you will get here, and also for the same thing for the negative x value, right? Now let's understand how we can use symmetry, how symmetry works. Notice that if we connect everything, so we know that it goes in this fashion, right? We know that the graphs go in this kind of fashion. And also in the positive direction, we can connect all these points. It will move like this. Now check this out. Notice that there is x-axis symmetry, right? Because this graph is reflected through the x-axis. You see this is the mirror image, this part, which is mirrored here in the through the x-axis, right? Now also there's y-axis symmetry, like we confirmed algebraically, because this image is a mirror one of this one, right? You can definitely say that this is a mirror image of that one. It's reflected through the y-axis. And also there's an origin symmetry. Now origin symmetry means that basically whatever point you have, well, let's say this point, radical 7 and 4, you get a negated version of that. Negative radical 7, negative 4, right? So let's see. So negative radical 7 is here, negative 4 is there, and that's exactly what we had. You see? And for every single point, the origin symmetry will be confirmed, right? So the origin symmetry means that whatever you get here, you will get a mirror image in the quadrant 3. So quadrants 1 and 3 will work together, and quadrants 2 and 4 will work together, right? Because they will also be reflections of each other through the origin. Okay? So quadrants 1 and 3 and 2 and 4, right? These will be the pairs that you will have to identify. When it comes to the y-axis symmetry, it's quadrants 1 and 2. When it comes to x-axis symmetry, it's going to be quadrants 1 and 4, or 2 and 3, right? And for the x-axis symmetry, for the y-axis symmetry, it's not only 1 and 2, but also 3 and 4, right? So you have to understand these pairs that you're going to use for every type of symmetry when you're graphing. But as you can see, this is the correct equation. This equation really works, and you understand, you confirmed everything that you've done algebraically with the way it looks, with the visual part of it. Right? So this is the equation of y squared minus x squared is equal to 9. Now let's move on to the next equation here. Now this equation is looks more complicated, but it's not that bad. You just have to follow the regular procedure. So first, the x-axis symmetry test. We have to negate the y. So negating the y. Now keep in mind that when you have a minus y inside the absolute value, you can break up the minus 1 by itself, multiply it by the y, and then subtract absolute value x, right? So you're breaking up the absolute value of negative y into the absolute value of negative 1 times an absolute value of the y. So that gives us what? That gives us, now you know the absolute value of negative 1 is simply negative of the negative 1 times the absolute value y minus absolute value x. So that what that gives you is the negative version of the negative is positive. So there you go. Positive 1 times absolute value y is absolute value y minus absolute value x. Look what happened. We matched the original equation. So we'll definitely know there's x-axis symmetry. Now let's test the y-axis symmetry. I'm going to negate the x value. So absolute value y minus negative of absolute value x. Absolute value of negative x is equal to absolute value y minus, now let's split again, absolute value of negative 1 times absolute value of x. So what that does is absolute value of y minus, now minus, we have to negate the negative 1, right? Negative of the negative 1 times absolute value x. So what that does is absolute value y minus, now negative of negative 1 is positive 1. Positive 1 times absolute value of x is absolute value of x. Good. So that means, again, you're matching the original left side. Good. So that means this has y-axis symmetry. Now the x-axis symmetry test, let's test that. You're going to negate both the y's and the x's, right? So I'm going to save some space this time. We know that the absolute value of negative y, as we've said, was the same thing as absolute value of y. If you do not understand, just go through what we did here. We took out the negative absolute value of negative 1, then we negated that negative 1, right? That's how it became positive 1 times absolute value of y. That's how we got it, right? And the same thing for the x. We know that the absolute value of negative x is the absolute value of x, right? So yeah, so this confirms that there's, just like in the previous example, there are three symmetries possible: x-axis, y-axis, and origin, right? So this is going to be an interesting graph. And something tells me that it's going to look very similar to this, except it's not going to be a quadratic type of, it's not going to be a hyperbola, right? It's not going to be a quadratic being reflected, right? It's going to be something else. It tells me that it's going to be similar to quadratic, but it's going to be linear. And as you can see, linear is related to absolute value functions, doesn't it? So that's good. So let's test the x and y intercepts. For the x-intercept, we set y to 0. So we're going to set this guy to 0. And then solve for absolute value x. So we get 3. What this tells you, if you divide both sides by negative, because this one's gone, the absolute value of 0 is 0, so you get left with this. This is the part you get left with. If you divide by negative 1, that means absolute value is equal to negative 3, right? Because you distribute the negative. But this has no solution, right? We know that because absolute value can never be negative, right? So no solution. And like in the first example, no solution means no respective x-intercepts, right? No x-intercepts, right? Because there was no solution. Now for the y-intercepts, we're going to set x is equal to 0 and solve for y, right? So y minus absolute value 0 is equal to 3. So that tells you that absolute value of y is equal to 3. Now there are two possibilities. Y is equal to 3 or y is equal to negative 3, right? Because this is absolute value. Okay, so that tells you there are two y-intercepts, right? Two y-intercepts. Y-intercepts. So we will have them at 0, 3 and 0, negative 3. All right, so let's plot them while we can. Okay, so if we plot them, we will get them here, 0, 3 and 0, negative 3. Okay. Now again, we're going to test some x values here. So when x is equal to 1, let's see what we're going to have. Right? When x is equal to 1, we just substitute x with a 1, we will get this, right? So absolute value of y is equal to, we're going to add 1 on both sides. We're going to have 4. So y could be theoretically 4, or y could be negative 4. Okay? And the same thing for negative 1, right? Because when x is equal to negative 1, the absolute value of negative 1, as we showed before, was positive 1, right? And you can use actually many tricks, right? You can use the algebra using the symmetry that you've shown before, or you can just use logic, right? You know the knowledge of absolute values, you'll be fine. So when x is equal to 1, we will have 4 and negative 4. Okay? And also when x is negative 1, we'll get the same thing, 4 and negative 4. Okay? So since since there's no other power for the x and y but 1, we know that this has a linear relationship. Right? So we know the graph will look pretty much like this, right? It will grow linearly to the left, and it will grow linearly to the right. Something like this. And the same thing here, right? It will go down linearly, and it will go down linearly, like this. Okay? So as you can see, look what happens. There are no x-intercepts, right? The graph does not touch the x-axis as we suspected. Just like in the first case, there were no x-intercepts, like the no solution showed. Here the same thing. And as you can see, this is a similar picture, except it's linear and it's not quadratic, right? But it has the same conformations of the x-axis and y-axis and origin symmetries, right? When we said that x-axis symmetry meant that we're talking about quadrants 1 and 4 and 2 and 3, it makes sense, right? Because we have x-axis symmetry, right? These are mirror images of each other. These are mirror images of each other. Also, we have y-axis symmetry, right? Because these two are mirror images of each other, and so are these two, right? And when it comes to the origin, remember that whatever the x and y coordinates you have, you will have the negated versions of them in the mirror image to the origin, right? So 0, 3, negated version is 0, negative 3. 1 and 4, the mirror image is the coordinate is going to be the negated version of 1 and 4, which is negative 1, negative 4, right? And that's precisely where we are. So if you understand these points, if you understand how symmetry works and how to confirm symmetries with the graphical representation of these functions, these equations, you will be fine, right? So as you can see, this is really not that difficult if you understand how to use certain points and then confirm your results by using intuition as well as understanding what each graph refers to and what it's most similar to. As you can see, the absolute value is most similar to the linear function. The hyperbola equation here that we've drawn here and analyzed is similar to the quadratic equation, right? So the absolute value equation serves here, double absolute value equation, serves as mirror image of a single absolute value equation that we know. But this one is a quadratic, but it turns out to be a hyperbola one when you're given this type of equation. So thanks so much for watching. Hope this helped a lot, and I'll see you in the next video.